The South African Institute for Aquatic Biodiversity relies on stereo-baited remote underwater video stations to collect video data. This data is manually annotated to identify and count different fish species, a time-consuming and labor-intensive process. This project proposes a deep learning-based framework, Fish ID, to automate fish identification and classification from underwater footage. We trained a YOLO V11 model to perform detection, after which each of us focused on different methods to perform species classification. My research explores how semi-supervised learning can reduce our dependence on labeled data when classifying fish species in underwater footage. I used vision transformers for classification and trained the model under 3 paradigms: fully supervised, semi-supervised, and semi-supervised with self-supervised pre-training. The results showed that the semi-supervised vision transformer performed best overall, excelling on both the common and the rare classes. Interestingly, self-supervised pre-training hindered the performance. While it improved general feature representations, it failed to capture the fine-grained features needed for species-level classification.
I decided to investigate a contrastive learning solution using Google's SimClear framework. Contrastive learning is a type of self-supervised deep learning, meaning that models are taught to learn useful features through unlabeled rather than labeled data. To use this framework, I had to collect a large unlabeled dataset. I sampled frames from the SAIAB footage at 1-second intervals, and used the detector to extract cutouts of fish specimens. Contrastive learning was generally successful as displayed in the bar chart on screen, with full fine-tuning of the contrastive trained model performing with the highest overall accuracy. However, further testing revealed that the fine-tuned SimClear model performed with a statistically insignificant difference to a fully supervised modern YOLO model. This result displays the extreme leaps in deep learning that have been made since the original SimClear paper was released in 2021.
For my implementation, I explored object tracking as a data augmentation technique. The provided dataset contained a large amount of raw video footage, but relatively little labeled data. The aim of object tracking was to better utilize this available data. Labeled fish were tracked across subsequent video frames, with each fish assigned a unique tracking ID. The labels were then propagated through the tracked frames, allowing the original dataset to be expanded. One concern was that test results would be falsely inflated if similar images appeared in both the training and test data. To mitigate this, an unseen test dataset was prepared. Overall, the object tracking data augmentation technique was successful. The model trained on the augmented dataset achieved a 13.4% top 1 accuracy increase compared to the model trained on the original dataset when evaluated on the unseen test data.